All right, in this video, we're going to talk about power functions and polynomials. And we're going to start with some definitions and something that we're going to introduce called end behavior, which we'll abbreviate EB. End behavior is going to be exactly what it sounds like. What is the behavior at the ends? All right, so let's start with a bunch of definitions. I hate definitions. I love definitions, all right? So to start off, some function g of x, if it's some constant times x to the n, that's what's known as a power function. Okay, so a power function is just a number, right? This is a real number multiplied by our variable raised to some non-negative integer. Okay, so n is going to be, right, n could be, I'll just write this. All right, it could be 0, it could be 1, it could be 2, it could be 3, etc. It has to be an integer, can't be anything in between those numbers. So we've seen power functions before. Let's look at some again, right? 2x, this is technically a power function. It's also a line, but that's with n equals 1. N could be 2. 2x squared, this is also a power function. 2x cubed is a power function to the 4th, to the 5th, to the 6th. To the 7th, what's happening? Notice what's happening every time we increase the exponent by 1. 2 is like this. 3 is like this. You can't see that much of me. But you can pretend. 4 is back to this, and then this, and then this, and then this, and then this, right? It keeps alternating between odds and evens. That's something that we're going to use. Evens all kind of behave like parabolas. 4, 6, 8, 10. They all have that same shape. They're just getting flatter in the middle and steeper at the sides. And the odds all kind of behave like cubics. But again, getting flatter in the middle and steeper at the sides. We're going to use that later on in this chapter. So these are all examples of power functions, and we know with function transformations, if I added a negative here, it would just reflect it about the x-axis, flip it upside down. So those are power functions. Another definition is if we just add up a bunch of power functions, that's called a polynomial. So f of x equals a sub n, x to the n, plus a sub n minus 1, x to the n minus 1. And so on, until we get to the first a, x to the first power, plus the last a, x to the 0th power. Any number to the 0th power is 1. All right, this is polynomial function. So just adding up a bunch of power functions. Whoa. All right, so that's mostly what we're talking about in this section. Power functions, and then a lot of things about power functions and polynomials are going to be very similar because polynomials are just a bunch of power functions being added together. Some other definitions. N is the degree for this polynomial. All right, so the degree is the highest exponent. Highest exponent of our variable. It's not necessarily always the first exponent unless it's written in the right form, but it is the highest exponent right here. And then similarly, right, a sub n x to the n is what's known as the leading term. And very, very similarly, this doesn't necessarily mean the first one, right? This is the number and the variable part that has the degree. So it's the term or the power function with the degree in it. And again, not necessarily the first one. We'll see where that comes into play later. All right, and finally, a sub n, that's just that number part, is the leading coefficient. And again, just like I've been saying a billion times on this page, it's only first if it's in the right form. All right, it's not necessarily the first unless it's in the right form. So watch out for that. All right, so let's do a little discovery and introduce the idea of end behavior. Okay, so if we look at some polynomials, again, all a polynomial is just a bunch of power functions added up. There can be missing terms. So right here, this is a polynomial. There's no exponent of 3 or 4 or 1 or 0. So we can add any numbers of power functions together. And notice, look at the end behavior. Look at how this function behaves at the end. So it's got some curves in the middle, but eventually it goes up to the left and down to the right. Now let's add another term, or let's add another term. Let's say 3x to the 4th. Different stuff going up in the middle, but to the left, it's still going up to the left. It's still going down to the right. Let's add a term 1x. Okay. What about 100x? Oh, that was a bad idea. That made it really hard to see. 1/10x. Let's subtract 55. Again, it doesn't matter what I'm doing to this polynomial, the end behavior is always the same. It turns out that the end behavior only has to do with the leading term. So as long I can add whatever power functions I want, as long as they have smaller exponents, and the end behavior won't change. Now, if I change this leading term, yeah, the end behavior is going to change. What if I make this leading term positive? So it's like this right now, but if I change the sign, what do you think is going to happen to the end behavior? Shoo. All right, the end behavior flips. Similarly, it's odd right now, so they're going in opposite directions. All right, that was pretty bad. If I make the degree even, what's going to happen? Hey, the degree is even. Now the end behavior, it's going in the same direction on either side. All right, so let's formalize that. If I can find my way back to the right window. So we can formalize that with a little table. Let's look at the end behavior. Whoa, I don't think we want it in green. I like green though. Wait, it's still green. End behavior, otherwise known as EB, because I hate writing the long things out. We can make a little table. It's like we're playing tic-tac-toe. Okay, so if the degree is even, then the end behavior is like a parabola. What do I mean like a parabola? Well, if the leading coefficient is positive, then it's like a parabola with a positive coefficient. This is how we're going to write it. It's kind of like a parabola, and then I'm just drawing little squiggles in the middle. And this just means we don't know what's happening in the middle. But if the degree is even, it's like a parabola. And if the leading coefficient's positive, it's like a parabola going up. Well, then how do you think this changes? If the leading coefficient is negative, it's still like a parabola, but now it's like a parabola going down. And again, we write squiggles in the middle because we're only looking at end behavior. We'll talk about local behavior in 5.3, what happens in the middle. And if n is odd for the end behavior, this is technically end behavior of polynomials. then it behaves like a cubic function. Remember, our cubic function looks like this. So if it's odd and positive, it's like a positive cubic function. If it's odd and negative, it's like a negative cubic function. And it's okay to draw or to answer end behavior questions with these little pictures. I think this is very helpful and informative. But as especially people going on into calculus, will be using other notation. This is what's known as arrow notation. So let's look at this one specifically. Arrow notation says that as x goes to the right, as x goes to infinity, what does the function do? Well, as we're moving to the right on this graph, what's the function doing? The function's going up to infinity. Similarly, as x goes to the left, as x goes to negative infinity, what's happening to the function as we're going to the left? Function's going down to negative infinity. And you could do these with all four of these graphs. And just again, how this is pronounced, as x goes or tends to negative infinity, that's how that is pronounced. Sometimes you'll see this as the word tends as well. There's also another notation. I know there's so many definitions and notations in this video so far, but it's good to have them down. This next one is going to be optional. Arrow notation is mandatory, but one is going to be optional, very helpful for people going into calculus. We're going to say the limit as x goes to infinity of the function equals positive infinity. The limit as x goes to negative infinity of the function is negative infinity. And again, these are both examples for this specific case right here. And then there's a small thing that technically the limit doesn't exist, but we write that it is infinity. But that's a technicality for a calculus class and not this one. All right, so just a bunch of notations. So you got pictures, you got arrow notation, you got limit notation. They're all different ways of talking about end behavior. And these last two actually can be used for other things as well. But for now, we're going to talk about end behavior. So let's just do some examples. All right. Example 1. Find. Actually, there's only one example. Find the degree, leading coefficient, and end behavior of the following polynomials. F of x equals 3 plus 2x squared minus 4x cubed. Be very careful. Like I was mentioning over here, leading term and degree. These are all things that are not necessarily first, even though we say leading. What we really have to look at is the degree, the highest exponent. So we start by finding the term, which one of these terms has the biggest exponent of x. Underline that, or rewrite the function. Underlining is quicker, but they're both valid ways of doing this. This right here is our leading term. This tells us our leading coefficient. This tells us our degree. All right, so our degree is that highest exponent of our variable. Even if there was like an exponent here, right, that wouldn't be our degree because that's not an exponent for a variable. It just changes the number. Looking for the exponent on the variable. The leading coefficient, that is the coefficient, the number next to the variable on the leading term. It's -4. For the end behavior, we can write our answer 3 different ways here, unless it specifically asks for arrow notation. I'm going to show all 3 different ways of writing our answer. All right, so we know that our degree is odd, and our leading coefficient is negative. So to look at our end behavior, degree is odd, means we're at one of these two. Leading coefficient is negative, means we're in this one. So where's the overlap? Well, we're in this situation. It looks like that. All right. And that's how we answer. Like a negative cubic. Or you could answer in arrow notation. As x goes to infinity, our function goes to negative infinity. As x goes to the left, our function goes up. These are all great answers. And if you really want to be on top of things, you can use the limit notation. The limit as x goes to positive infinity of the function equals positive infinity. And the limit as x goes to negative infinity of the function. Oops. As we go to the right, it goes to negative infinity. And as it goes to the left, it goes to positive infinity. Wow, I am really losing it today. So again, this last thing is optional, but can be good practice. All right, and that's end behavior. I'm going to write down 2 more problems on the board, the metaphorical board, and metaphor's not the right word. And what you are going to do, hopefully, is pause the video and try to solve these problems. Let's see if we get to the same thing. G of t equals 5t to the 5th. That's not a 5. 5t to the 5th minus 2t cubed plus 7t. And part C is h of p equals 6p minus p to the 4th minus 2. And then we'll look at these together and do one final problem. So feel free to pause the video, try to get these ones down on your own, and then let's see where we have. All right. First, we identify the leading term. The leading term is the term with the variable that has the highest exponent. The degree is that highest exponent. So the degree here is 5. And the degree here is 4. The leading coefficient is just the number that's the coefficient, the number next to the variable in the leading term, which is 5 here and -1 here. So again, here our degree is odd and our leading coefficient's positive. That tells us that our end behavior behaves like a positive cubic. In the second one, our degree is even, and our leading coefficient is negative. That tells us it behaves like a negative parabola. Kind of like so. In arrow notation, as x goes to the right, the function shoots off to infinity. As x goes to the left, the function shoots off to negative infinity. As x goes to the right, the function goes to negative infinity. Well, and as x goes to the left, it goes to negative infinity as well. That's B. And that's C. Let's do one more trickier question together. F of x equals 3x squared times x minus 1 times x plus 1. This is not in the right form. The degree is not 2. Okay? There's an easy way and a harder way to find the degree. In 5.3, we'll talk about one way to find the degree using the concept of multiplicities. There are 3 zeros here. There are 3 roots at 0, +1, and -4. And then you just count those exponents that go with each one to find that this is degree 4. Or you can just multiply this one out. So if you multiply this one out, that's what we can do here. First, outer, inner, last. We have to do all these pairs here, FOIL it out. And it's going to look like so. And then collect like terms and then distribute once more. So this is the most straightforward way of approaching this sort of problem. But there are some tricks that we'll talk about in the next section as well. You should get 3x to the fourth plus 9x cubed minus 12x squared. And now we can identify this is the degree, this is the leading coefficient, this is the leading term, all this stuff, and end behavior. Should get a degree of 4, a leading coefficient of 3, and the end behavior, well, it's even. Whoa, not EV. Even degree, positive leading coefficient. End behavior is going to look like a positive parabola. And you could use arrow notation as well. That's how you do these sorts of problems. Last thing I want to do, that I would highly encourage you to do whenever possible, is let's check our answers on these. Let's look at part A. 3 plus 2x squared minus 4x cubed. What's the end behavior for this one? Up to the left, down to the right. Is that what we had for A? Up to the left, down to the right? Good, we had the right end behavior. What about part B? Part B said g of t was 5t to the fifth minus 2t cubed plus 7t. End behavior, maybe zoom out. Yeah, it looks like it's going like this. Up to the right, down to the left. Up to the right, down to the left, good. What about C? Part C is h of p equals 6p minus p to the fourth minus 2. It's going down on both sides. Down on both sides. Good, 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 good. And this last one, f of x equals 3x squared times x minus 1 times x plus 4. Yeah, I typed this in wrong. 3x squared times x minus 1 times x plus 4. It's going up in both directions. It's a little harder to see here, but if we zoom out in the y direction, make y down to negative 100 to 50 or something, you can see it a lot better when you zoom out only in the y direction. If you zoom out in the x direction too, it'll get a little harder. All right. So all of our end behaviors are right. This is what end behavior looks like. Definitions of power functions, polynomials, leading coefficients, leading terms, degrees. So much information in this first video. But the future ones should be a little more straightforward and have more concentrated examples. So hope you enjoyed it. Hope you love graphing things. Hope you like polynomials. Hope you like algebra. And if not, we'll survive it together. Let me know if you have questions.